This video is going to cover higher derivatives, just a brief intro, as well as an application of derivatives. So we have learned that the derivative is the instantaneous rate of change, or the slope of the tangent line. We can denote the derivative using the notation y prime, f prime of x, or dy dx. We can find something called the second derivative, which is the derivative of the derivative. And the second derivative gives us a rate of increase or decrease. It tells us how quickly is the slope changing. Is the function increasing at an increasing rate or a decreasing rate? And we'll talk a lot more about the second derivative when we talk about graphing a little bit later. But the notation we're going to use for second derivatives is y double prime, or f double prime of x, or you might see d squared y dx squared. All of those things mean the same thing. You're finding the derivative of the derivative. And you can continue. You can find a third derivative, a fourth derivative, etc. So a third derivative, y triple prime, or d cubed y dx cubed, etc. So let's just take a look at a quick example. We have the function f of x equals 3 divided by x to the fourth plus 5x to the third minus 2. Let's find f double prime of x. Let's find the second derivative. So first thing I'm going to do is just take that 3 divided by x to the fourth and rewrite that as 3x to the negative 4. And then the only way to find our second derivative is to find our first derivative, and then we take the derivative of that. So the derivative of my function, bring down the negative 4, I get negative 12 x to the negative 5, plus, and then for the 5x cubed term, bring down the 3, 15x squared, and 2 is a constant that has a derivative of 0. And so to find my second derivative, I just take the derivative of my derivative. So bring down the negative 5, I get 60x to the negative 6, and then bring down the 2, and I get 30x. And that would be my second derivative. We could rewrite that first term as 60 divided by x to the 6. Well, we don't have to, but sometimes it's helpful to have positive exponents. All right, second part of this problem asks us to find f4 of negative 1. That little 4 there actually means the fourth derivative. Once we get to higher and higher derivatives, usually past 3, it's kind of a pain to write 4 little primes. It just gets sloppy. It takes up a lot of space. So when we get to higher derivatives, sometimes we'll just put a little number in parentheses above the f. And so that f4 of negative 1 means we want to find the fourth derivative at x equal negative 1. So my second derivative from the previous part was 60x to the negative 6 plus 30x. So then for my third derivative, I take the derivative of that, I bring down the negative 6, negative 360x to the negative 7, and derivative of 30x is 30. I'm going to find the derivative one more time. So my fourth derivative, bring down the negative 7, I get 2,520 x to the negative 8. And then that second term, that 30, is a constant, so has a derivative of 0. So there's my fourth derivative. And then to find my fourth derivative at x equal negative 1, I'm just going to plug in negative 1 for x. I did move the x to the negative 8 to the bottom and made it an x to the positive 8. So 2520 divided by negative 1 to the 8th is 2520. All right, so we can take higher derivatives by just continuing to take derivatives of derivatives. And in this video, I want to show you one specific application of higher derivatives, of the second derivative, but we'll continue with this topic a little bit later on as well. So the one application I want to show you has to do with position, velocity, and acceleration. So if the function we're working with represents the position of an object, where is an object at a function of time? We'll call that s of t. When we take the derivative of the object's position, that's actually going to give us the velocity of the object. How is the position changing with time? Gives us velocity. We can call that v of t. If we take the second derivative of our position, which means we're taking the derivative of our velocity, that's actually giving us acceleration. It's describing how the velocity is changing. So it's giving us information about whether our object is speeding up or slowing down. So let's take a look at an example. We have a diver jumping from a platform. Her position in feet after t seconds is given by the function s of t equals negative 16t squared plus 16t plus 32. Find and interpret v of 1. So v stands for velocity, so that means we have to find the derivative of her position at t equal 1. So position function, I'm going to take the derivative of my position function, bring down the 2, I get negative 32t plus 16. That 32 is a constant, so it doesn't put anything in our derivative. So my s prime of t is a function that gives me the velocity of the diver as a function of time. To find the diver's velocity at t equal 1, I'll just plug 1 into that function. So negative 32 times 1 plus 16 is negative 16. Now, since her position is in feet and t is in seconds, this derivative, or this velocity, should be in feet per second. So her velocity is negative 16 feet per second. The negative part is telling me that she's moving in the negative direction, which in this case I would assume is down. So this is telling me that she's actually going down. That's what the negative tells me. And then the magnitude, or the absolute value of your velocity, is your speed. So this is telling me she's going down at a speed of 16 feet per second. If I had gotten a positive velocity, that means she's going up. All right, well, what about a of 1? Acceleration is the second derivative of my position. So if I look at my position function, s prime of t, the derivative of negative 32t plus 16 is just negative 32. There's nowhere to plug in the 1, so s double prime of 1 is negative 32, and my units are going to be feet per second squared. This is an acceleration. This is telling me how my velocity is changing. So because my acceleration is negative, that means my velocity is actually decreasing. Now in this case, since my velocity was negative as well, if my velocity is decreasing, getting smaller, that means my velocity is becoming more negative. And so the diver is actually speeding up in that downward direction. In this particular case, this negative 32 actually represents the acceleration due to gravity. It's negative because gravity is really pulling the diver downwards. Let's do one more application problem. What is the diver's velocity upon impact with the water? So to solve the last part of this, we have to figure out, well, when does she hit the water? So we want to know velocity when she hits the water. So when does she hit the water? Well, that's going to be when her position is equal to 0. We can assume that the water or the ground is our 0. So I'm going to set my position function equal to 0. And I have a quadratic equation. Negative 16t squared plus 16t plus 32 equals 0. We could use a quadratic formula. I think we can factor this one. I'm going to pull out a negative 16, and then I'm left with t squared minus t minus 2. And let's see, product of negative 2 is 2 and 1. If I make the 2 negative and the 1 positive, that does add up to negative 1 in the middle. So I've got two solutions, t equal 2 and t equal negative 1. In this context, t equals 2 is the only one that makes sense. It doesn't make sense to have a negative time. So that means she must hit the water after 2 seconds. And so what this problem is actually asking us is, what is her velocity after 2 seconds? And I've already found my velocity function in part A. It was s prime of t is negative 32t plus 16. So now I'm just going to plug 2 into that function, and that gave me negative 48 feet per second. So negative tells me she's still going down. Well, that makes sense. She's diving down into the water. And her speed, or the magnitude of the velocity, has gotten a little bit bigger. As she's going down, she's getting a little bit faster and faster. And that's due to that acceleration due to gravity. All right, that was my last example. Let me know if anything in this video is unclear.